This video explores the anatomy of solar power, from the microscopic interaction of photons to the construction of commercial solar arrays. We'll examine the physics, variables, and architecture of photovoltaic systems. The core principle involves 3 steps. First, photons are absorbed, dislodging an electron. Second, the p-n junction creates an electric field that forces electrons and holes to opposite sides. Third, this separation creates a voltage difference, allowing direct current, or DC, to flow through an external circuit, doing electrical work. A single crystalline silicon cell produces a small output, typically 0.5 to 0.7 volts, and 1 to 2.5 watts of peak power. To achieve utility-scale power, we must understand the environmental variables that limit this baseline output and scale up accordingly. Several factors affect output. Irradiance determines current, while temperature causes voltage drops. Shading creates a bottleneck, and the light spectrum limits usable light. Scaling from a single cell to a full array requires connecting many cells in series and parallel to meet power demands. Irradiance, or light intensity, directly drives current. More photons mean more current. However, voltage remains stable regardless of light intensity. Therefore, most of the change in total power from varying sunlight comes strictly from changes in current. Temperature limits power output. As cell temperatures rise above standard test conditions, the intrinsic band gap shrinks, causing a sharp drop in open circuit voltage. Voltage drops roughly 0.32% to 0.4% for every 1 degree Celsius increase. Good mounting design that allows airflow is key to preserving voltage. The silicon band gap acts as a wavelength filter. Photons with wavelengths too long lack the energy to free an electron. Photons with too much energy shed the excess as wasted heat. This physical reality limits the theoretical maximum efficiency of a standard silicon cell to about 1/3 of the sun's total incident energy. The shading bottleneck is governed by the weakest link rule. Because cells within a module are wired in a continuous series chain, they must all share the exact same current. A small shadow on a single cell can bottleneck the entire string, dragging the current down to match the weakest performing cell. System design should minimize shading. The bypass diode is the solution to mitigate shade. When shaded, a cell reverses polarity and absorbs up to 6 to 8 volts, risking severe damage. The diode activates when a string is choked by shade, sacrificing that string's voltage entirely, but saving the massive current of the overall panel. Physics limits a single silicon cell to about 0.5 volts. To achieve utility-scale power, we must master series and parallel architecture to geometrically combine cells and meet the massive voltage and current demands of the modern world. Step 1 is cell to module, building voltage through series connection. Wiring positive to negative adds voltages together, creating an additive effect. The current remains the same as a single cell, a static effect. Encapsulating 36 to 72 cells creates a weatherproof module. Step 2 is module to string, matching the inverter. We continue the series connection at the macro level. Wiring 10 to 20 modules in series creates a string, stacking their voltages to push the system into the inverter's optimal operating window, typically 300 to 600 volts DC. Step 3 is string to array, building volume through parallel connection. Wiring positive to positive and negative to negative across independent strings keeps the system voltage identical to a single string, a static effect. However, the total system current multiplies with every added string, a multiplier effect, creating the final array. This architecture matrix summarizes the scaling. A cell provides the baseline, vulnerable to high temperature. Modules multiply voltage and are vulnerable to single cell shading. Strings further multiply voltage, creating a shaded module bottleneck. Arrays multiply current and are limited by the central inverter capacity. In summary, the output is a delicate balance of irradiance driving current and temperature draining voltage. The vulnerability is shading, as series wiring makes the system only as strong as its weakest illuminated link. The engineering uses series connections to build necessary voltage and parallel connections to build necessary current for massive solar arrays.